Now we have a fundamental understanding of a qubit. We can also do some logical operations on our qubit. We learned about the NOT gate. We learned about the Hadamard gate, which puts it into superposition. And we also figured out that fundamentally it's what frequency you fire at our qubit system that makes the electron jump from one energy level to the next energy level, and also by doing that changing the spin of the electron. Now, that's not much of a computer, so we should have worked out by now that we also need a control computer to go with our qubit measurement system, or our qubit calculation system. So there's my control computer, and we'll call that our classical computer. And then within the computer, of course, we have memory. So here's a memory map. And then within all that memory, there's registers. So if we consider this register here, in the classical computer, we have the ability to set that to a 1, or we have the ability to set that to a 0. What we want to do is write that bit value. So we want to perform a write operation first to our to our qubit. So the journey is as follows. First of all, we have what we would call the microwave control and measurement system here. So this is a microwave section. Microwave, because it's all about generating frequencies. And within this system, we would have some way of generating a pulse. And we would also have some form of synthesis to generate the microwave frequency, and we would mix those together using a mixer, an IQ mixer in most cases, to get the correct control pulse to control the qubit. The next thing is the qubit itself is housed in what we call a dilution refrigerator, and this is essentially a unit that absorbs heat. It's got 3 stages. So room temperature is, say, 300 Kelvin. And in the first stage, we're down to 1 to 4 kelvins. And then the next stage down, it gets colder the further you go down, 100 to 800 millikelvins. And then here in the bottom, it's the coldest part, and that's 4 millikelvins. Say 4 to 15 millikelvins. And absolute zero is 0 kelvins. So we're very close to absolute zero. And when we're at this temperature here, this is where superconducting occurs. And our superconducting qubit, which is the qubit we're examining today, has to be cooled, so it starts to have superconducting behavior. So in control, we're going to send our pulse frequency down. It's probably going to be some attenuation blocks on the way down here, down to the qubit. And the attenuation is to ensure that we've got the lowest possible noise on the signal. So we take it down to a point where we're eliminating as much noise as possible. And here's the qubit itself. I'll just write the Q for qubit there. And when we send the frequency that says let's jump up an energy state and invert our spin, we'll create a pulse of a certain frequency, energy level, excited energy level minus ground state energy level over Planck's constant is the frequency, and we'll set the bit. Now, if we want to do a read function, it's the opposite. So it's kind of the opposite, but it's not. But first, we'll send another frequency that represents the measurement frequency. So a write is control, and a read is essentially control and measure. So we'll set a frequency. It says we're going to measure this thing. The qubit essentially is a bunch of resonators. And the first thing that happens is we have a couple of amplification stages. We have the quantum amplifier, and then we have one a little cooler. Again, noise, KTB, Boltzmann's constant. The lower the temperature is, the less noise we have. So it's good to have an amplifier down here, and it's good to have an amplifier a little further up. So we set our control bit, and then we get a measurement result, and that would go to another mixer here. There's an oscillator here. These two are probably phase locked. And then a DAC. Sorry, an ADC. An ADC, my mistake. An ADC, so we can get a DC reading. When we measure it, we're probably going to get one of two answers. A spin up could be represented by a phase shift. A spin down could be represented in a phase shift in the opposite direction, or it could be frequency shifts. So say we stimulate it with like 7 gigs, 7.1 gigs could be a spin up, 6.9 gigs could be a spin down. So we set the register. By setting the register, it generates an appropriate microwave signal, a microwave pulse. It sets our qubit into the appropriate spin state. When we want to read it or collapse the quantum state, we send another signal into it, and we look at the output. And if it's a spin up, if it collapses to a spin up, it's going to be a certain frequency or phase shift. And if it collapses to a spin down, it's going to be another frequency or phase shift. So in the next video, we're going to take a look at the actual circuit representation of what a qubit looks like.
Tabor Electronics, a high-end, world-leading signal source company.